is it running? Good morning. So this is a review session. I hope you're feeling a bit ready for the exam. And as you see, today's session will be filmed because I heard people can't make it to today's lecture. So we'll film the whole thing and post it online. But I want to emphasize that you might feel shy because the camera to ask questions, but you shouldn't. I mean, it's fine to feel shy, but ask the questions nonetheless. All right, so what I'll do today is go over some exam type questions. Some are directly from the exam, some are somehow inspired by the exam. And I'll start with a few integrals. So right, that's the structure today. Just showing you how to solve questions. Question one, find the following indefinite integral. Integral of arctan x dx. And so one point I want to kind of make through this exercise is the arctangent is an inverse function. So if you have there's some list of inverse functions. One big member of the family is ln, others are arctan, maybe arcsine, and arc cosine. And so the punchline is inverse functions differentiate easily. Because look at this, what we have here. I just want to check, by the way, did we do this in class already? We didn't, right? So inverse functions differentiate easily. What I mean by this, so ln and arctan and all this are kind of difficult to grasp. But look, if you differentiate ln, you get 1 over x. It's just fairly simple, and arctangent will give you 1 over 1 plus x squared, and there's the derivative of the arcsine and the arc cosine, and they become substantially easier when you differentiate them. And this holds in general for inverse functions. And if you're confused, by the way, about this name inverse function, look what happens to this. If you take x, you apply ln to it, and then you apply e to the result. Like you raise e to the power, which is ln of x, you get back the original thing you started with. And this is something somehow people don't really realize. If you do, fine. If you don't, yet think of what ln of e should be, or ln of e squared. And ln of 1. If you don't really know what I'm talking about here, there should be somehow an alarm bell, and you should think of those two cases. Once you get those, you're fine. But this is what an inverse function is. You apply one function, then you apply the second function, and that's essentially doing nothing. Having said all this, we have here the indefinite integral of an inverse function. which is complicated. We want to somehow make it easier by deriving it. And then there's this trick to use integration by parts in the following way. So the function we want to derive will be arctangent. And then remember, I always write f for the one we derive, and then g prime for the rest, which is the function we'll integrate. Thing is, there is no rest really, so we just write a 1. And we recognize this as the integral of 1 times arctangent. Well, g primes is 1. G can be x. I mean, g could be x plus 2 too, but we want to keep things simple. And now we use integration by parts. Find that the integral of 1 times arctangent will be f times g, which is arctangent times x, minus the integral of f prime times g. Well, f prime is 1 over 1 plus x squared. G is x. And we're left with this integral, so this is a minus. So let's do the second integral separately. The integral of x over 1 plus x squared. In this case, what you can see is that if you ignore this x for a second, you see a function of a function, namely 1 over x, and subsequently 1 plus x squared. Yeah. So you want to use a substitution, but you need to recognize the derivative of the thing you're substituting with somewhere. Well, if you said u equal to 1 plus x squared, then u prime will be 2x. And up to this factor 2, we recognize as x here. So this sort of screams at you, please apply a substitution to me. So this will be, so if u prime is 2x, du will be 2x dx. In this case, maybe I want to take the 2 to the other side. So we have du over 2 equals x dx. So this x dx, this x on the top gets absorbed in the dx, and we're left with the integral 1 over u du. Which in turn, I mean, we can pull out the half. Let's just do it all in one go. Look, we pull out the half. The integral of 1 over u, you know, it's ln of u. We have half ln of, don't forget the absolute value brackets, ln of the absolute value of u, plus c, and then to finish, we write back for u what u originally was, which is 1 plus x squared. And so, need more space. So the integral of arctangent, we established already that this is x arctangent of x minus the integral of x over 1 plus x squared dx. Integral of x over 1 plus x squared we calculated separately. If you plug it back in, don't forget that there's this minus here. We have to leave there. So we get minus a half ln absolute value of 1 plus x squared plus c. And that's the answer. You see, so the whole point of using this integration by parts is that we can differentiate this arctangent. Arctangent is complicated. If you differentiate it, it becomes easier. And the same line of reasoning you want to apply to the integral of ln of x, the integral of our cosine of x, or maybe our sine of x. This was an exam question a while ago. But also, if you have something like x squared ln of x, I think what I wanted to write was actually x ln x squared. Here again, you see, well, a function x and an inverse function ln squared. So you want to use integration by parts again to make sure you derive this ln thing. I think we did the integral of ln squared in class a while ago. You have to actually use integration by parts twice to really get rid of this ln by differentiating. Any questions on this? Right. Question 2. Let's do an indefinite one. Improper. Evaluate the following improper integral, or show that it diverges. Integral -1 to 0, 1 over x plus sine x dx over x squared. First question for you, why is this integral improper? I mean, it has finite bounds. There's no infinity on top, there's no minus infinity on bottom.
Because it's not continuous.
Where? At 0.
Yeah, 0.
I mean, you have the right idea, of course. If you see improper somewhere, you know that the integral is improper because of the question, and there's no infinite here, so it must have an infinite discontinuity. And indeed, if you plug in 0, sine of 0 is 0, x squared. If you plug in 0, you get 0 squared, which is also 0. You get 1 over 0, which is not allowed. So how to do this? Well, usually I keep on saying first replace this problem point by a t. That's what I usually tell you. So I replace the 0 by a t. Write limit t going to 0, in this case from the left. This is important. Because it's a right bound of integration, we want to approach it from the left. And then you would, I mean, this is a usual tactic, then you would consider this integral as a usual finite proper integral and work with that, finding an antiderivative, plugging in the bounds, which happen to be t and -1, and then take the limit of that. However, I don't really know how to integrate this. I could find an antiderivative. So I'm just thinking, if you're in your exam, maybe you think of this, because I kept repeating it. Okay, replace the problem point by t, write the limit, etc. And then you maybe get stuck, because you don't really know what to do, and I wouldn't blame you, because this is a very difficult integral. So if you think, if I just simulate you or myself being on the exam, I would think, go through the methods, right? Known integral, no. Integration by parts. Wow, I don't see how that makes my life any easier. Substitution. I mean, I have a function of a function, 1 over something, but I don't recognize the derivative of second something anywhere. So problem. And what you might realize then is that we're dealing with an improper integral. And we either need to evaluate it or show that it diverges. So showing that it goes to infinity is a perfectly fine answer. And once that is our goal, showing it diverges, we can use all sorts of comparison theorems. Right? So remember, if some function f is greater than or equal than a function g, and the integral for gx with some boundary point could be infinite, or we think for the moment, I'll just think of this as an improper integral. If this diverges to infinity, look, so g is big enough for the integral to diverge to infinity. Well, f is even bigger. So whenever g diverges to infinity, so does f, using the same boundary points. This is a general technique. So maybe we can compare this to something which is easier to work with. Question?
Yeah, so we're going to compare it to 1 over x squared, and then we can have like a p-series and prove that it diverges? Or
How about the sign? Because 1 over x squared is actually.
Let me just get, you have to,
X squared.
the right idea.
sorry.
So, no, it's fine.
Because
Uh-huh.
if you plug in like -1 on sine of x, it's gonna give you a negative value. So it's gonna be greater than 1 over x squared.
Yeah, you guys are killing. Yeah, that's how you should do it. Let me show you. So, as Ian pointed out, so draw a little graph here. This is 0, and sine of x looks like this. -1, minus pi over 2 here. But you see, 0 is here. Sine of x on this interval integration, that's very important, is negative. So on this interval, -1, 0, sine of x is smaller than or equal to 0. So x squared plus sine of x is smaller than or equal to x squared. We're subtracting something, essentially. I did this on purpose to somehow confuse you. I put a plus here. But this sign is negative. So you're really subtracting, you're decreasing the value of x squared by adding the sign on this particular interval. And so what we get is that 1 over x squared plus sine of x is greater than or equal 1 over x squared. Very sorry, I believe I would get away with not pointing this out, but I made a mistake. Guys, I'm very sorry about this, but I have to change the question in order for it not to be wrong. I'm going to replace the x squared by the absolute value of x. Same principle applies everywhere. Nothing of what I said is going to change.
But what's the difference? Because anyways, x squared is always positive.
No, that would be conversion. That would be conversion.
Problem is that this is not part of the exam problems. But if I put x squared here, I'd be dividing by it. But sometimes this number is negative.
How?
Yeah, that's part of what I wanted to avoid explaining. So I'm very sorry about this. So I'm happy to explain you why. But maybe that's best left for after class. Can we just pretend I wrote absolute value of x all along? It's just if someone would look back to this, you guys probably wouldn't notice, but it's just wrong what I'm writing. I don't want to write wrong stuff. Anyway, same thing applies. We realize that sine is negative. So we have this, and we have this, and now we're very happy. Because we can compare our function here, which is complicated, to something which is easier. So consider the integral -1 to 0 of 1 over the absolute value of x. Let's just calculate this. Using this method that I keep saying should be the first way to go, usually. So 0 replaced by t. We write limit of t tending to 0 from the left. And the same integral. And now we're just trying to define this integral, this finite integral first, and then take the limit of this as t tends to 0. Well, first thing you can do is realize we write 1 over the absolute value of x. But we're on an interval where x is always negative. That's one reason why it's important to let t approach 0 from the left. And so, in that case, the absolute value of x is equal to minus x. Right, so if x is smaller than or equal to 0, the absolute value of x is equal to minus x. The absolute value of the absolute value of minus 5 is equal to minus 5. So what do we get? Limit t approaching 0 from the left of this integral here, and look, we wrote it before. The integral of 1 over x is ln. So the integral of minus 1 over x is minus ln. Minus ln t. Sorry, minus 1 of x. Minus ln of x is an antiderivative, and I evaluate this at the boundary points. Last step before we can play with the limits will be plugging in these boundary points. So this will be minus ln of the upper bound, which is t, minus ln the lower bound. Oops. See, now I get to the point where I'm confused. But let's make this democratic. Do you see the mistake I made? I actually emphasized this earlier in the previous question. So the integral of the indefinite integral of 1 over x is not really ln of x, but it's ln of the absolute value of x, right? So this is good because I said it in the previous question, now we said it again. I made the mistake even, so that means you probably won't forget it on the exam. And you see why, when I realized this, I wanted to write ln of minus 1. I realized it's impossible. Take a step back. Right, so ln of the absolute value of x. I plug in t, so this is minus ln of the absolute value of t, minus the ln of the absolute value of x, of minus 1, which would be 1. And now I have to take the limit of t tending to 0 from the right to this. Which is a great opportunity to remind you what the graph of ln looks like, which also is something I noticed people can't spit out where they should. Ln goes like this. Oh. Ln of 1 is 0. So this is x equal 1. An important point of this is that ln has a vertical asymptote, goes to minus infinity, at x equals 0. So here we're taking the limit of t tending to 0. So this ln here will go to minus infinity. But we have a minus ln. So this guy will go to positive infinity.
Since we're evaluating the limit by the left side, we can see that does not exist the limit, right? Because if the right side,
If you want, maybe it's a good point. So I wrote the graph of ln. Maybe I should have drawn the graph of ln of absolute value of x. Oops. And that one, so ln normally is not defined on the negative part. But if you put this absolute value, any negative value you plug in will be transformed into a positive one.
So you just finish like that?
So you sort of mirror image it
That's minus 1.
like this. This is the graph of y equals ln of x. Yeah.
And then you're approaching from the left side.
In this case, we're approaching from the left, but you know, before it was important, now, I mean, whatever side you're approaching from. So, the limit of t tending to 0 from ln minus ln of the absolute value of t plus ln of 1. By the way, what's ln of 1? 0. Very good. This limit is infinity. Or we say it diverges to infinity. And this is very good news because we got a bit digged in over here, but remember our goal was to compare this complicated function that we didn't know how to integrate to something which is relatively easier and hope that this will go to infinity. Because if this would be a finite number, we wouldn't be anywhere. But luckily, the indefinite integral of 1 over x is diverging to infinity. So let me write that down. So the improper integral of minus 1, 0, 1 over absolute value of x plus sine of, yeah, like this. This diverges to infinity. Since 1 over absolute value of x is smaller than or equal 1 over absolute value of x plus the sine of x, we conclude the improper integral minus 1 to 0, 1 over absolute value of x plus the sine of x dx diverges to infinity too. And that answers the question.
Should it be negative infinity?
Why should it be negative infinity?
The graph goes to negative infinity.
Yeah, so this is the graph of y equals the ln of absolute value of x. And we're taking the limit, it's a good point, taking the limit of t tending to 0 on the left, of minus ln of the absolute value of t. So if you like, I can also draw the graph of minus ln. It's just flipping. So in pink will be the graph of minus ln of absolute value of x. You see, I'm just flipping. Minus ln. You can also think of it this way. If this minus wouldn't be here, we'd have a minus infinity. But then we have a minus. So it's like minus minus infinity in a way. Just basically. You had a question?
Yeah, over there, when you have the 1 over the absolute value of x, and then you have minus 1 over x. I guess that has to be with that orange square.
This stuff.
Yeah.
It's because of this.
Okay. And that's just like that.
Look, so here we think of x as a negative number. Usually I say minus 5 in this case. No, minus 5 is not the integral, but think of it as minus 5.
Okay.
Minus a half, if you like. If x is minus a half, I have minus a half, and this will be a positive number. So this is why the absolute value of x equals this. This is in general a trick we use. If x is positive, absolute value of x is equal to x. If x is negative, absolute value of x is equal to minus x.
I have a question.
Yes.
Could we just, if we have that in the exam, just assume that we know that 1 over absolute value of x diverges, or we have to do the whole thing and say like, no, I know this.
Well, so I can only tell you what how I would mark, right? And it might be that someone else is marking. But I would want to see this.
Right? And if we say like it's a p series with 1.
Ah, right. That's good. Yeah. Thank you for reminding me. Because, look, if the integral would be improper because of one of the boundary points being infinity, this would be like a piece series in a way. Because if you think of a piece series, it's either some 1 over n to p and it starts at 1 to infinity, or it's the integral from 1 to infinity, 1 over x to p dx. These series are really concerned with behavior going to infinity. You see there's an infinity for sum and infinity for integral. Whereas this is, I agree that it looks like a p series, but the thing that makes this integral improper is really that that it goes to 0 here, which has no counterpart in series. So, short answer, no, this is not like a series. And maybe a nice exercise for you, if you want, will be to calculate this guy. Integral improper, let's make it easy, don't do any negative stuff, just 0 to 1, 1 over x squared. I'm pretty sure this diverges too. Whereas if you think of it as a p-series, going to infinity should converge. More question? Does that answer your question? Oh yeah, just something I want to say. Please, 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 if you, exclamation mark, if you have a definite integral, like maybe 3 or s, and you use a u substitution like this, u would be x plus 1, I guess dx is du. Don't write this. Please, don't.
No. Can we just leave it as improper, and then when we come back to the function?
Yeah. I'll come back to this. So, do you guys see the problem first? This. If you have a definite integral and you use a substitution, you should apply the function u to the boundary points. So, u is x plus 1. So, u of 4 would mean 4 plus 1 is 5. And we'll have 5. And here we have to apply u to 3. U adds 1, so we'll have 4. And then you go from there. I won't show you because we know how to do this. Just nominate this point. And as Ian points out, you can either work with this and solve this and get a number, or you can first solve the indefinite integral using u sub in whichever way you like. Once you have the indefinite integral, just use that as an antiderivative and never worry about boundary points. And what I saw in the midterm is that most people prefer this strategy. But it's a really silly way to lose points, I find. Of course, it's fine to be silly. But let's say it's an easy way to make points. Maybe that's a better way to phrase it. All right, volume. Question. Sketch the region enclosed by the graphs y equals 2x squared, y equals x cubed, and find the volume of the solid obtained by rotating. So if you read this question on your exam, this is where you sort of maybe tense up. Are we going to rotate along the x-axis, or a translation of it, or along the y-axis? And unfortunately, we are rotating along the line x equals minus 1, which is vertical. So this is more difficult. Let's show you how to do this. I know a lot of you have been working on volume problems, so that's great. Let me show you how to do this. So maybe some steps. First, of course, we have to sketch. And we have to find the intersection points. It should be part of a good sketch, but we'll need those anyway for the rest of the question. So we really can't skip them. And since we're rotating around a vertical line, we have to make the step of interpreting x as a function of y. And then thirdly, finding big R and possibly small r. If it's a disk, we'll just it will suffice to find a big R, but we might have to find a small r too. So first sketch. And so some general points. If you look at something like y is equals x squared, if I would look at the right quadrant, so sorry, it's fine. Y equals x squared goes through the point 1, 1. And looks something like this on the right quadrant. If you take a function with a higher power, y equals x to the power 5 or 50 or whatever, you would find it still goes through this point, but sort of steeper. This is how you can think of these exponential things. The higher the exponent, the steeper it goes. So the tighter it touches the x-axis before lifting off, and when it lifts off, boom, it goes. But it always, if it's of this form, it always goes through this point 1, 1. And so that's one point I want to make. This is general guidelines for sketching. If you have something y equals x to the power even, so x to the 2, x to the 4, x to the 6, it will look globally something like this. So up on both sides. And by the first point, if the exponent is higher, it will stick to the x-axis more and then explode very steeply. If the exponent is odd, you have something like this. I think there's t-shirts where this guy goes like x cubed, x squared, and then sine, whatever. X cubed, x squared. So how to draw this? These things are things you should always keep in mind when sketching. Basic behavior of polynomial functions. And so now that we know this, the first one is easily found. This will be y equals x cubed. And then let me see, y equals 2x squared. So it will be something like this. But since we multiply by 2, it sort of gets stretched outward. So should be something like this. And look, I wouldn't blame you if you don't know whether this goes on top or bottom. You can always ask your calculator. You can even plug in x equals 1. Then y equals 2 in the pink case and y equals 1 in the white case. And you know the pink must be on top. And to complete the sketch, what are the intersection points? If you want to find the intersection point of curves, you set one curve equal to the other, so this y should equal this y. So I'll have intersection points x cubed equal 2x squared. And take the 2x squared to the other side, you get x cubed minus 2x squared equals 0. It looks complicated because of the power 3, but then you realize you can pull out a factor x squared. And we'll have this x squared times x minus 2. So x equal 2 or x equals 0 or x equals 2. And if x equals 2, you plug it in either one of these graphs. In both cases, you get y equals 0. Did it say x equals 2 again? If x equals 0, you plug in the value in either one of the graphs. You get 0 everywhere. If you plug in 2, you do it in either one of the graphs. In both cases, you get y equals 8. And so these are the intersection points. So this is the point x equals 2, y equals 8. And here, 0, 0. And this is a sketch. Or maybe let's draw this this line. X equals to minus 1. It's here.
Okay. So,
And the region, maybe we also want to fill this in. Sketch the region enclosed by the graphs. So the region, maybe I can use green. Make it even more happy. The region is this.
but also the little triangle between -1 and 0.
No, but I'm very happy you asked this. Question is also the little triangle here. Why is this not part? Let's look at the question. Sketch the region enclosed by the graphs y equals 2x squared, y equals x cubed.
Because it's not enclosed by those two.
This guy, this is the axis of rotation. But if you just look at the region, it's only given it should be enclosed by these two graphs.
Okay.
So for the finding the region, we don't care so much about this line. We only look at those two graphs.
Right. Then what would affect? What would be the difference between x equals -1 or x equals 0?
This is the axis of rotation. We're going to rotate this green area along this axis. And you'll see it pop up when we find r and
So then will it affect the general volume?
yep, let me show you. You will see when we do r and big R and little r. So we finished the first point. Now we want to interpret x as a function of y. And there's two ways to go. You can either keep the sketch and sort of integrate along the y-axis, or you can just rewrite the whole question, interchanging x and y everywhere. Let's try that. Interchange x and y. The graphs now will be x equals 2y squared, x equals y cubed, and the line now is y equals -1. So you see why we want to do this interchanging step, because now we reduce to the case where we just rotate along something parallel to the x-axis. Maybe you want to take a 2 to the other side. Y squared will be x over 2, meaning y is the square root of x over 2. In this case, you can go straight to final step and see that y is equal to the cube root of x. You see, so I'm flipping x and y and then rewriting again so that y is really a function of x. And just a quick sketch. Essentially, we're flipping this picture. So it'll be something like this. And like this. So this will be y equals square root of x over 2. Y equals cube root.
Question?
Yes.
Well, why do you do that?
Why I do this?
Yes, because if you were turning around the x equal -1, the same thing that you turn around the vertical line y, right? So I don't understand why you were doing that.
Well, so look, the axis of rotation.
Well, I guess I don't add like -1 to the formula.
Yeah, but like so. One sec. Y equals -1. If I want to find the integration, the area here, I'll have to integrate with respect to y. And people find this really confusing. I mean, some people are happy with this, and others just look at me. What are you talking about? So I want to show you how you can reduce this situation to the situation where you integrate it with respect to x.
Okay, but if I want just continue using like Like that, I can use the same formula and add -1 and continue the integration.
If you integrate with respect to y,
Yeah.
you'll be integrating along the distance. If you're comfortable doing this, perfect.
Can we do both?
If you have a lot of time in your exam, yeah.
Oh, it takes a lot of time.
I mean, then you'll be doing the same thing twice.
No. Can we do both now to see the difference?
Ooh, I would rather do some more stuff.
Just one?
Shouldn't there be y equals to positive or negative square root of x over 2, so we have the bottom part as well?
Very good question. So the question is really like, where did this part of the graph go? Right. So usually you should account for that, but that's why I drew this graph this way, and I chose the question like this because the area is only concentrated in the upper quadrant where both x and y are positive. So in terms of finding the area and stuff, we only care about this part.
One question.
Yes?
If we integrate the graph on the left, isn't the interval 0 to 8?
Yep.
And on the right, wouldn't it be 0 to 2?
I don't think so. Let's see, because everything gets flipped, the x and y. So this was the point 2, 8. This will be the point 8, 2. This is 0, 0. You'll see that in the end you're doing the exact same thing. Exact same thing. Just flipping x and y, but the procedure is exactly the same.
It looks like on your graph, the upper function and the lower function are switched to, so we're subtracting like one from the other differently.
No, so if you would take the first method, you would think of this as the radius. This would be your big R. And you see, so the white one is the upper one. Whereas here, oh sorry, it should go all the way to here. Whereas here you'd be drawing your big R like this, and white one is still the
Because
top one.
when you integrate with respect to y, you take the rightmost graph and you subtract it from the leftmost.
Exactly.
But with x, you take the upper, so subtract it from the lower.
Exactly.
Oh.
I like that. That's good. So let me,
So somebody missing to what you see.
but yeah, really, this is a method of doing this. And if you're already comfortable with the first one, that's fine too. So we did the second step that I drew in the outline. Lastly, we want to find R, big R and small r. So big R will be the distance from the top function to the line y equals -1. Let's see. And small r will be the distance from the lower function to the line y equals -1. So let's see, big R. This distance here, from the y function to the x-axis, is given by the graph, by the function. So this is cube root of x. Then we have to add 1, because we go one step down from the x-axis. So big R will be cube root of x plus 1. Right, so cube root of x is this first step. We go to the x-axis, and we go one more down. And we add 1. So likewise, small r will be the distance from the pink function to the line y equals -1. Same procedure. So to go from the pink function to the line to the x-axis, that will be square root of x over 2. And then we have to add 1. So now we have a formula. Pi integral r squared, capital R squared minus small r squared dx, which in this case is, I'll write x to the power third plus 1 squared minus x over 2 power half plus 1 squared. You see, so I'm writing these as 1 over 3 and 1 over 2 in preparation for what's coming. Because if I work this out, oh, sorry, I forgot something, right? Refers to what you mentioned earlier, Nick. But the boundary points of integration. So what are they? Let's see in the graph where the volume starts here, the area, sorry, which is x equals 0. It goes all the way to here. And the x coordinate of this intersection point is 8.
Well, in the other side would be 2. Yeah. No. Yeah.
If you want, you can also recalculate it. Or you see, if you plug in 8 here, let's see, 8 over 2 square root will be square root of 4, which gives me 2. Whereas here, if I take the cube root of 8, I also get 2. So you see these two functions do agree on the point x equals 8. So here we have 0 and 8. 0 and 8. And from now on, it's just procedural. So this is the integral 0 to 8 of x to the power 2/3 plus 2x to the power 1/3 plus 1. This is working this out using the binomial formula. Minus this whole thing. So this will be x over 2 plus 2 x over 2 2x to the power half over the square root of 2. Right, so I'm taking this exponent a half out. Plus 1 dx, which is the integral from 0 to 8. When we order this, we have half x minus a half x plus x to the power 2/3 This is not the best way to do it, sorry about this. So first I want to simplify, then I want to find an antiderivative as usual. So simplification here is not such a big deal, I'll just copy the thing. But so look here, I have a plus 1, and here I'll have a minus 1. So they'll cancel. Which is very nice. So I'll have minus x over 2. And then here, if you look at this, so 2 over square root of 2. If you think of 2 as being square root of 2 squared, one of the square roots cancels against the square root in the denominator, and you get minus the square root of 2 x to the power half. Finding an antiderivative of such functions is fairly easy. You add 1 to the exponent, and you put the new exponent in the front, but invert. So here we have x to the power 5 over 3. I'm adding 1. I have to invert the exponent and put it out front, so I'll get 3 over 5. Here I do the same. I add 1 to the exponent, get 4 over 3. I have to put 3 over 4 in the front. There's already a 2. So I have 3 over 2. Same here, I have an x. I have to raise the exponent by 1. I get a 2. Put a 1 over 2 in front, but I already have a 1 over 2, so I'll have a 1 over 4. And finally, minus x to the power 3 over 2. I'll get 2 square root of 2 over 3. And we have to evaluate this at the endpoints. And then, well, look, so this point, it's fine to ask your calculator. If you're like me and you're in front of the class without the calculator, to do a bit more work. So maybe, can you guys still see it if I write here? Can you get some nodding or shaking hands in the back, maybe? Nodding, great. So we'll plug in 8 and we'll plug in 0 and we'll subtract the results. But you know, if we plug in 0 everywhere, we just get 0. So we don't need to bother. We just plug in 8 everywhere and that's our answer. So 3 over 5, 8 to the power 5 over 3. I'm using that the cube root of 8 is 2. So we have 2 to the power 5, which is 32. So again, you can use your calculator for this. I don't have one right here. Same here is cube root of 8 is 2 to the power 4 is 16. 1 cancels with the 2. 3 times 8. Minus a quarter times 8 squared, which is really 64. And this one is a bit more involved. Because we'll be taking the square root of 8, which is really 2 square root of 2, and then cubed. What do you think? 8. I believe this is 16 square root of 2. So you get 2 square root of 2 over 3. 16 times square root of 2. And then you work this out. And you simplify this. And let's go on because I want to do some series and sequences. Are there any questions on this? Yes.
Just one question. If you were to do it in the original graph that you had drawn,
Right.
the boundary points, would they also be 0 to 8 because you're looking at your y values?
Exactly.
Okay.
Okay, that's good. Big R is the one on the farthest.
Yeah, there's so many questions, I'll draw this now. I'll recalculate.
I know, but if you're looking for the farthest one, the farthest one.
A bit like this. Here's my yellow. This was point 2,8, right?
Yeah.
This one should be your big R.
Yeah.
So going to the wide one. This one to the yellow, pink one will be your small r.
And still plus 1.
Yeah, because here you have the line x equals to -1.
Okay. So it would be like x cubed plus 1,
Okay, let me see if we can pull this out.
2x squared plus 1.
Yeah, it's like this. Whoever wants to talk about this, let's do a mini meeting about it after class and we discuss it in detail. More questions before I raise stuff.
Does anyone else feel like their head's gonna explode?
Sorry?
From this noise? Someone's like vacuuming like a whistle outside or something?
Yeah, I'll check.
Stand up. Stand up and society. Can't focus on anything else? What is that thing?
He was vacuuming some stuff. Right, let's do some quick sequences. Find the limit of the sequence an as n goes to infinity, or prove that it does not exist. 1. an equals to cosine of n over n. If I see this personally, I think 1 over n, that's great. It might go to 0. Oh no, there's a cosine here. Really annoying. This cosine is somehow, we know what to do with it. If it's cosine of pi, or cosine of 2 pi, pi over 2, but this will be cosine of 1 and 2 and 3. And we think of this cosine as annoying. We want to get rid of it. And then we use this. This is a trick. We've seen this before. If you take a sequence and you see that the limit of n tending to infinity of the absolute value of an is 0, the limit of the absolute value is 0, then the limit of the sequence itself is 0. This makes sense. If the absolute value of the thing gets smaller, then it means the thing gets super close to 0. And so that applies in this case. Let's see how we get this to work. So this absolute value of the an, which is the absolute value of cosine over n. See, I'm not writing absolute value of n because we know n is positive. Now comes the trick. Cosine, same for sine, of any value is usually always in between 1 and minus 1. Since we take the absolute value, we know for sure it's smaller than or equal to 1. And we have this. Now we want to use a squeeze theorem. We want to find bound an from above by something that goes to 0. That's what we did. But in order to show that the limit of an itself also goes to 0, we need to bound it from below as well. In this case, there's a very easy bound. An is always, the absolute value of something is always bigger than or equal to 0. So, since the limit n tending to infinity of 1 over n equals 0, and the limit of n tending to infinity of constant sequence 0 is also 0. So you think of this as a sequence, but a constant sequence. It's 0 for every an. We find that the limit n tending to infinity of the absolute value of the an is 0 as well. It's bounded from above by something that goes to 0. It's bounded below by 0, so the thing itself goes to 0. And so don't forget to write this last step. So also the limit n tending to infinity of an without absolute value brackets is 0. Something you should not forget. And there was this exam question which was, I think it was a sine instead of a cosine, and then there was this minus 1 to the power n. It's minus 1, it was just there to confuse you. Or to sort of nudge you into using an absolute value bracket.
So you have minus 1, what changes?
If you would have minus 1 to the n?
Yeah.
Well, think of what happens if you take the absolute value of this.
It's just 1.
becomes useless.
Sorry?
I said if you take the absolute value, the negative 1 just doesn't matter anymore.
Exactly, so the exact same thing would have applied if there would have been a minus 1 here. So that's easy. Okay, so that's good. Let's do one more. Oh yeah. So same question, only a different sequence. An equal 2 to the power 3n plus n squared plus 3 over 6 to the power n. So we need to either find the limit or show that the limit does not exist. And so the point I want to sort of hang up on this question is that when you see this sort of convoluted thing with multiple types of growth, so we think of this 2 to the power 3n and the 6 to the power n as exponential growth, because the variable n is in the exponent. And here n squared plus 3, n squared is quadratic, the variable is in the bottom, 3 is constant. So these are both polynomial growth. And when you have such a question, you want to look for the one that's most dominant in a way, the most dominant type of growth behavior. And in general, you have exponential growth dominates. I'm writing a greater than or equal sign for dominates anything polynomial. Whereas polynomial dominates anything with log. I'm just making a general point out of this. And this factorial dominates anything that's exponential. I know this is relatively new information. I just want to give it to you. If it confuses you, feel free to just brush it off, because it's not technically part of what you should know, but it's very useful in the sense that when you look at a sequence like this, you should sort of scan for the one that's the most dominant. And in this case, I see 2 exponential growth and some polynomial type growth. So then I want to think of this an. This is very informal. This is just to make you realize what direction you should be heading. Think of an as 2 to the power 3n over 6 to the power n. I'm just deleting everything that's less dominating. And so here, this 3n is there to make you realize that you can rewrite this as 2 to the power 3 to the power n, where 2 to the power 3 is 8. And we'll have a 6 on bottom still, which is 8 over 6 times to the power n. If this were the sequence that you were given, would it diverge or would it converge or something? Diverge. It's a number, positive number, bigger than 1. So if you keep on multiplying it with itself, it keeps on growing. If this were 6 over 8, it would go to 0. If it were 1, it would be constant 1. Those are the 3 cases. So now we expect this guy to go to infinity. And so maybe it's useful if we can compare it to something simpler that does go to infinity. And so, well, something simpler is right there.
The metric series?
I heard geometric series, but it's not really a series, right?
Oh, yeah.
Now, it's very common to confuse them, but don't confuse series and sequences, so it's good that you pointed it out. So in this case, I can just say, look, n squared plus 3 is always greater than or equal to 0. So an is greater than or equal to 2 to the power 3n over 6 to the power n. But the limit, n tending to infinity, as we just argued, of, maybe I'll write, equals 8 over 6 to the power n, to make this more of a sentence. An is bigger than 8 over 6 to the power n, but the limit of n tending to infinity of 8 over 6 to the power n, so infinity, diverges to infinity. And so this is very similar to here, except that here I was stressing really that you should bound it by something from below and from above. Here we only bounded it by from below, but since the thing on below goes to infinity, there's only one way an can go. So now we don't need to bother about bounding it on 2 sides. So limit n tending to infinity, an equals infinity as well. So that's very good. Questions on this? So we're getting very close to the end, so I'm just giving you this guy and just giving you a hint. If you ever see a question of this type on n squared plus 1 over n minus 1, I'll just tell you what to do. You want to set a function ln of x squared plus 1 over x minus 1. And then use L'Hopital's rule over this limit. So copy this, write it down, look at the video, and then look at it yourself. And this is a general principle. If you see something, a fraction, a quotient, ln of something over x something, you could see your life would be much easier if you differentiate both sides, because the ln is considered complicated, but if you differentiate it, it becomes easier. And so this is why you want to use L'Hopital, but L'Hopital you can't really use for sequences. You have to first define a function. It doesn't work always, but in this case it works. So this is a general technique. This is my point that I'm making. So very quickly, series. Determine convergence type of sum minus 1 to the n plus 1 squared over n times the square root of n to the power 5 plus 3n. And usually the question is more like determine whether it's convergent or divergent, and if it's convergent, determine whether it's absolutely convergent or conditionally convergent. So let's see, again, I don't want to show you this question, but explain to you how to think of these type of questions in general. So if we set an, just focus on the positive part right now, or maybe I'll write bn, because that's what we're used to. If bn will be the positive part of this series, right? So now we are in this series. Following this dominating stuff that I just mentioned, we see mostly polynomial type things going on. This square root that we don't really know what to do with. And now if you want to think of bn in a certain way, what you want to do is take only the highest powers of n. In every instance where you see something with n. So what I mean is there's n plus 1. Don't think about the square for a second. The highest power in this n plus 1 is just n. So we delete the constant. So we'll have n squared. There's not much to do. There's an n. Then the square root of n to the power 5 is 3n. We want to think of this again as n to the power 5. You only consider the highest exponents of n. So we'll have to leave the square root there, like this.
So why did you write the single n?
Sorry? 2. So this is n squared over n times n to the power 5 over 2. So I'll have n to the power 7 over 2. Which is n squared minus 7 over 2. It's really 4 minus 7 over 2. N to the power minus 3 over 2. Or if you like, 1 over n to the power 3 over 2.
Isn't it just 5 over 2?
Times n. Yeah, you see there's a specter n there that you multiply the n to the power 5 over 2 by.
Yeah, but I thought we were only choosing the highest degree. N is degree 1.
Yeah, but you do this process of choosing the highest degree in every instance. You do it only once. From that point, you keep them. You essentially, you only want to get rid of stuff that you plus with, that you add. Here we add 1, but we already have an n, so we get rid of the 1. Here we add 3n, we already have an n to the power 5. And here there's no plus, there's a multiplication. Right, so the point I want to make is, and you'll see why this makes sense. Maybe it comes a bit out of the blue now. You'll see why this makes sense. If we think of bn as this way, first of all, what do we expect? So this is a p-series, if you would plug this back in. 1 over n to the power 3 over 2. with p equal to 3 over 2, which is higher than 1. So we sort of expect convergence. And so the way to make this rigid is to use, I'll write that in orange again because it's a reminder, this limit comparison test that I wanted to bring up because it's been a while. If you have two sequences, let me write Bn and Cn, and the limit of Bn over Cn is equal to some number, let me write C, B, bigger than 0, so a finite number but not equal to 0, then convergence, maybe I write it like this, then the sum of Bn converges whenever sum of An does. So if sum of Bn converges, so does sum of An. Oh, sorry, I should write it Cn. If sum of Bn diverges, so does sum of Cn. And this is interchangeable. Do you have a question?
Yeah. So you use the limit comparison test, but if I decide just to use the comparison test, sees that all the factors on the series, they are positive, so it allows me to use the comparison test, right? Instead of just use the limit, I just can use comparison test. But if there is a negative over there, I wouldn't be able to use the comparison
Not really,
test.
because you're dividing by this, right? So n to the power 5 plus 3 will be bigger than or equal to n to the power 5. Since you divide by it, it will be smaller than or equal. So you have a right idea. If there would be a minus here, boom, go for it. But that's why I'm using this example, because that's the first thing that would come to mind. It doesn't really work. You can make it work if you're really creative, but it will be a bit more hard work. But it's a good point. And so the point I'm getting at, because I wrote this limit comparison test, I made you cook up this Bn out of the blue. And the point is that you want to compare this this guy here to this guy. So we want to take the limit, n tending to infinity, of this n plus 1 squared over n times the square root of n to the power 5 plus 3n, and divide it by the thing we found here, 1 over n to the power 3 over 2. And this whole process of keeping only the highest exponents, the highest powers of n whenever you see them, is actually designed so that if you do this, you get a finite number. You'll get 1 actually. And you always get 1 if you follow this procedure. So it is time. So let me first come to the conclusion. Then of course, whenever you have questions, you can still ask me in class. So I invite you to work out this limit. We'll see. You know what we'll do? I'll just say it's 1. I'll give the conclusion. Then people, if you want to leave, if you need to leave, you can leave. But I'll show it for those who want to stay here. Right, so assuming that we did this calculation, you want to write something like, since 1 is a positive or a non-zero finite number, and since the sum 1 over n to the power 3 over 2, n tends to, and starting at 1 to infinity, converges, and maybe you want to write something like p series with p equal to 3 over 2, strictly larger than 1. So the marker knows that you don't randomly decide it converges because it's convenient to you, and you hope that it's correct, but you actually know what you're doing. the limit comparison test tells us that sum n starting at 1 up to infinity of n plus 1 squared over n times the square root of n to the power 5 plus 3n converges. We're not completely done, because our original question had a -1 that I took out for convenience, but of course we have to account for it. So if I put it back, -1 to the n plus 1 squared over n square root n to the power 5 plus 3n converges, and then I need to put another word. What's the word? Absolutely. So this is really the convergence type of this question. So by the lack of people leaving, I assume you all want to see the limit. I mean, yes.
In which case it would be converging, what do you say?
Conditional.
Conditional, yes, sir.
Conditional convergence means that this guy converges as a series like this, but if you if you take the absolute value, it does not converge anymore.
Okay.
And the standard example is,
But here we didn't take that first value. We don't need to.
well, secretly we did. I didn't say it so explicitly, but when I passed to the Bn, I erased this -1, so I took the absolute value.
Oh, okay. Because each term there is positive. So, okay.
Yeah, I think n is always 1 or higher. So this is 2 or higher, this is 1 or higher, this is very high.
Sir, in the orange section, shouldn't it be the other way around? When Cn converges, shouldn't Bn converge?
Oh, this is a very good point. Everybody pay
If
attention.
Bn
So
is larger?
it goes both ways. If Bn converges, Cn converges. If Cn converges, Bn converges. If Bn diverges, Cn diverges. If Cn diverges, Bn diverges. It goes every single direction that you can take.
V being larger than 0 means Bn is over Cn. If it diverges, Cn has no obligation.
Right. Okay. So I think you're thinking of a comparison test. This is a limit comparison test. But if you would have Bn larger than Cn, like this, with no information on the limit. For example, maybe n squared larger than equal to 1. That's not exactly n squared larger than equal to n. If you take the quotient of this and the limit, you won't get a finite number. But it is true that n squared is larger or equal than n. And so in this case, sum of Cn diverges implies sum Bn diverges. In this case, what you say is true, that if Bn would diverge, you cannot infer divergence of Cn. But this is the comparison test, whereas this is the limit comparison test, which is in a way stronger. And here it goes both ways. Yep. Okay, great. So, this is unfortunate. So this limit n plus 1 squared over n square root of n to the power 5 plus 3n over 1 over n to the power 3 over 2. This is very similar to how I taught you to apply this ratio test for power series, in the sense that we want to invert the second fraction. So I'll keep the n1 squared over n times n to the power 5 plus 3n. And I'll multiply by the inverse of this fraction. The fraction is itself n to the power 3 over 2 inverted. I'll have n to the power 3 over 2. Let me simplify. N to the power 3 over 2, n plus 1 squared over n square root n to the power 5 plus 3n. I didn't do anything, I just wrote the n to the power 3 over 2 on top of the fraction. And this is a technique from Cal 1. Here again we want to divide by the highest power of n that you see. And it's a bit tricky to find the right power of n to divide by, but you think again of this n plus 1 as an n squared. So the power of n you see on top is n squared times n to the power 3 over 2, which is really n to the power 7 over 2. And you see if you do that line of thinking to this guy on bottom, you see the same. Because we'll have, think of this as n to the power 5 square root, which is n to the power 5 over 2, but we multiply by n, so we get n to the power 7 over 2.
So it's 1 over 1.
Eventually it'll be 1 over 1. So you see, this is why we did this procedure here, to find this 3 over 2 essentially. So if you multiply by it, you get exactly something which is a finite limit. If you multiply by something with an exponent higher, you go to infinity. If you multiply by something with an exponent lower, you go to 0. So this 3 over 2 is exactly the right number to make it work. Long story short, so I'll divide top and bottom by n to the power 7 over 2. Power 3 over 2, n plus 1 squared over n to the power 7 over 2. Divided by n square root n to the power 5 plus 3n over n to the power 7 over 2. Equal limit going to infinity. So here a 3 over 2 cancels, and we're left with a 4 over 2, which is just an n squared. And we'll have n plus 1 over n squared. Here 1n cancels, we're left with an n to the power 5 over 2, which is the square root of n to the power 5. So I'm going through this step by step. On your exam, you might want to take it faster, but since I'm explaining, I want to make sure everything's clear. So on top, I'll get 1 plus 1 over n squared. On the bottom, look, this is a square root of something divided by a square root of something. I can think of this as a square root of n to the power 5 plus 3n over n to the power 5. Like a large square root sign covering it all. And we'll get 1 plus 3 over n to the power 4. And now we're essentially there, because I didn't say it, but, well, let me just say, look, if you think of 1 plus 1 over n, and n tends to infinity, well, 1 over n goes to 0. Same here. If n goes to infinity, n to the power 4 definitely goes to infinity. And 3 over something extremely large, it goes to 0. So we're essentially left with 1 plus 0. Move limit. 1 plus 0 squared over the square root of 1 plus 0, which is just 1. All right, so don't forget we have a question session or extended office hours next Friday, day before the exam. So if you have questions, come see me. If you don't have questions, you can also come and just sit there and listen to other people asking questions. And maybe that's useful too. So I wrote it on the board. It's also on Moodle. And I'll check if I need to change the room. So just a quick temperature check. How many of you are planning on attending? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Great. I'll let you know. So keep an eye on Moodle for the possible location.
doing December 17. So 한 exam 버스로 I don't know how to. So the person is tangent to cover.